Arnab Sen giving us this colloquium and visiting us virtually. After Arnab graduated from TIFR maybe a little over 10 years ago, he has had an amazingly diverse portfolio of research, starting with work done in Boston University with Anders Sandvik on some rather subtle quantum phase transition issues, which they resolved. After which he went to Dresden at the Max Planck Institute, where he got interested in dynamics and was part of a group of very active and pioneering sort of people who were doing all sorts of interesting things with non-equilibrium quantum dynamics over, in the early parts of this decade. And for the last few years, he's been at IACS, where he's continued some of this dynamics work and also developed another sort of branch of interests having to do with some interface between condensed matter theory and high energy physics. But today, I think he'll talk to us about the non-equilibrium dynamics work, or at least one aspect of it. So he's going to tell us about what have come to be called quantum scars in many body systems. So Arnab, over to you.
Okay, thanks, Kedar. So I'm very happy to give this colloquium, and I would have been happier if I could give it physically by visiting the TIFR campus, because that place is always dear to me. So nonetheless, so let me start. So before I begin the physics part, let me thank all my great collaborators. So I have been thinking about this issue of quantum scars in many body systems for about 2 years now. And I've had the opportunity to collaborate with various people on different aspects of this problem. And there are still many things which are open in the field. So I think it's rather exciting. So many of these people would be familiar to you, especially Deeptiman, Krishnendu, and Devashish, because he was also a graduate student in DTP around the same time I was there. And I would especially like to acknowledge the junior collaborators in this chain of work. So Bhaskar Mukherjee was a graduate student in IACS, and so was Shourabh Nondi. And in particular, lots of the work in particular, these 3 papers, they really benefited from Bhaskar's drive and expertise. And then there is some other work which I did with people who had close links with Max Planck Dresden. So I was visiting Dresden for an extended period in the pre-COVID era, and then we started talking, and yeah. And then more recently, I got interested in certain aspects of quantum scars in lattice gauge theory, and there I was really helped by talking and collaborating with Devashish, and I'll also talk a bit about that in today's colloquium. Okay, so let me start, and feel free to interrupt and ask questions at any point if something is unclear, okay? Yeah. So this is the brief outline of the talk. So I'll introduce the bare bones of something called the eigenstate thermalization hypothesis, which basically tells us how many body quantum systems locally equilibrate even in the absence of a heat path, external heat path. And then I'll go to the main focus of today's colloquium, which is quantum many-body scars and their consequences, which is something called a weak ergodicity breaking. And in fact, this field was, okay, the theoretical motivation came from a very surprising and interesting experiments, basically 2 years back in Lukin's group. So I'll very briefly tell you what that experiment was, and then I'll go to theory and introduce 2 quantum spin models in constrained Hilbert spaces. And these models are also interesting because they can be mapped exactly to Hamiltonian formulations of certain lattice gauge theories. So the first model is the PXP model, which is now sort of very well known in the community of people working on quantum scars. And so this is sort of the Ising model of the field, if you wish, because that led to a lot of developments. And I'll basically explain to you how one can qualitatively think of the quantum scars in this many-body problem. And then I'll introduce another many-body problem, which is this U1 quantum link model. And there we would see that there's a rather unusual effect, which we sort of dub as order by disorder, but in the Hilbert space. And finally, if time permits, I'll also talk about the fluke version or the periodically driven version of the PXP model. And there's something very interesting there, which is scars and they're melting. Okay, right. But let's see. Let's see how I go and how I manage my time. Okay, so right. So imagine that I have a closed quantum system, and for concreteness in this talk, we'll think of, let's say, lattice models with quantum spins residing on each side. You can think of spin half for concreteness. Okay, and let's say that the spins are interacting through some local in space Hamiltonian, so some short range Hamiltonian. Then the basic setup that I have in my mind is that I start with some very simple initial wave function, some wave function which is basically unentangled. Therefore, I can write it like this, okay, where these 1, 2, 3, and so on are basically the site indices. And then I let this wave function propagate by the unitary dynamics generated by the many-body Hamiltonian, right? So this is what it is. And then I focus on local in space operators, okay? So if you wish, I'm just focusing on a patch. Maybe this patch is one site or 2 consecutive sites or maybe 10 consecutive sites. But the important thing is that it's a local patch in a thermodynamic limit. And if you concentrate on such operators or correlation functions defined on this patch, then even though I am doing a purely unitary dynamics, if I look at such a local quantity, after an initial transient, this thing seems to attain a well-defined steady state value. And the steady state value miraculously mimics the answer that you would get from a thermodynamics or a Gibbs ensemble calculation, where the temperature is essentially set by the energy density of this initial starting state that you have. Okay. However, since I'm doing unitary dynamics, of course, I know that it's distinct from connecting the system to a heat path. And so I can always have certain operators which are rather non-local. For example, I have defined such an operator for you. So it's an operator like this, where these states EM and EN are many-body eigenstates of your Hamiltonian. And then for such an operator, it's very easy to verify that if you look at the time-dependent evolution, this would just do oscillations like this and would never thermalize. Okay, but the important thing is I'm just looking at local operators and I'm not looking at these highly non-local operators. Okay, so why does this thing happen? So this thing happens essentially because of the scrambling or the dynamics of entanglement. Okay. So the idea is that my initial wave function, which let's say I have prepared in my lab. Oh, by the way, I forgot to mention, in the past 2 decades or so, this field has been really boosted by several experimental platforms where such a dream of a theorist can actually be realized in a lab. So there are several beautiful experiments on various things like ultra-cold atoms, trapped ions, superconducting qubits, where till a certain reasonable time scale, which is large compared to the microscopic time scales of your interacting theory, you can actually imagine that the system is almost not coupled to the external world. So you're really doing this even in the experiments. Okay. So that has really provided a boost to this field, and lots of people have started thinking about theoretical issues here as well in the past 2 decades. So yeah, so what precisely happens here is that you start with a simple initial state. So let's say which has low entanglement. So these lines are supposed to schematically show your entanglement. And then you do some unitary dynamics. So this unitary dynamics, because it is unitary, of course, if you wish, in a loose sense, preserves quantum information. But what happens is, as you evolve the state in time, the state starts getting more and more entangled. And to actually glean out this quantum information, you need to, after a sufficiently long time, measure or probe some highly non-local operator. Whereas if you look at a local operator, then you effectively think that this memory of the initial condition is erased, but that is exactly what thermalization means in statistical mechanics. So this is sort of the resolution of how closed quantum systems equilibrate locally. And the more microscopic way of formulating this is the eigenstate thermalization hypothesis, which basically deals with the matrix elements of local operators. So this OA is a local operator, as I told you in the previous slide, because it has support only on a few sites in, let's say, a big spin system. So this local operator, if you actually write in the eigenbasis of your many-body Hamiltonian, you can easily write this left-hand side like this. So there are two classes of terms in this left-hand side, and these EIs and EJs are, of course, your many-body eigenstates. So one class of terms are the terms which sort of don't depend on time, like this. And there's another large class of terms which does depend on time. Now, ETH tells you something about both the diagonal matrix elements. So when I say diagonal, I mean this many-body eigenstate is the same as this many-body eigenstate, and as well as the off-diagonal matrix elements, by which I mean that this many-body eigenstate is different from this many-body eigenstate. So the precise statement of ETH is that if you look at the level of eigenstates, then basically your right-hand side looks like this, where this OA of epsilon, so this epsilon bar is basically like EM plus EN divided by 2, okay? And this omega in my notation is like EN minus EM, okay? The difference in the eigenvalues of the two many-body eigenstates. So essentially, this quantity, OA, is basically the microcanonical answer that you would have got by doing a statistical mechanics calculation when your energy is fixed by the energy density of the eigenstate. So this is a microcanonical thing, okay? And there is numerical studies on small lattices have already confirmed that. And if you wish, there's no analytic proof of the statement, but if you sort of go in the regime of semi-classics, then there is a sort of a proof. But if you move out of the semi-classical regime, then there is no strict analytic proof for the statement. But nonetheless, numerical observations and other arguments tell you that this thing should be correct. The second thing is, so when this state is initially prepared, there are obviously some transients. Now, this is also true for a usual stat mix system, right? So you take a usual stat mix system, it takes some time before it relaxes to its final equilibrium state. If you start with a state which is strongly out of equilibrium, right? So exactly something happens here also. And this thermalization, if you wish, is dictated by these cross terms. And ETH also has something to say about that. The first statement that it says is that these off-diagonal elements in a many-body system, a large many-body system with many degrees of freedom are very, very small, because this S here is actually the entropy, if you wish, the entropy in a microcanonical ensemble for, again, states which are centered at E bar, which is EM plus EN divided by 2. So you see, even though the left-hand side is a purely quantum mechanical quantity, the right-hand side actually contains information about the microcanonical ensemble, both here as well as here. Okay, and then there is also this F function, which actually tells you a lot. It tells you about basically the early time dynamics of this relaxation as well as the late time dynamics. So it has a lot of information about how specific operators relax when they are sort of started from very out of equilibrium states, and then ultimately they reach equilibrium. Okay, and these R's are some random numbers. Pseudo-random numbers rather. But okay, I can discuss this more if somebody is interested later, but this is sort of the nutshell of what ETH is. And all this setup actually ensures that many-body system locally equilibrates, even though there is no external feedback attached to it. Okay, good. So now we come to the topic of this colloquium. I said that most interacting theories equilibrate due to ETH. Now we can ask, what about theories? Are there theories, rather, which actually violate ETH? So the answer is yes. There have been two mechanisms which have been known for quite some time in the literature. So one mechanism is called integrability, which is a concept familiar to us very well from classical mechanics. And we also know that there is a quantum version of it, that even though this is slightly less understood. But roughly in integrable systems, for example, if you again want an example of a spin system, you can imagine the two-dimensional Kitaev model being an integrable system, or even in one dimension, there are various spin models which are Bethe integrable, or even the spin equal to half transverse field Ising model, which is again an integrable model. So integrable models are special. They are rather fine-tuned many-body Hamiltonians, where in fact all eigenstates, and not just the eigenstates close to the ground state, in fact all eigenstates in your spectrum have a quasi-particle description. And this basically tells you that ETH is violated in such a theory. So if you look at this numerical plot again, this is a plot of a bunch of hardcore bosons. Again, you can equivalently think of them as spin half degrees of freedom on a lattice, living in a one-dimensional line. And there is some nearest neighbor hopping of these hardcore bosons, and there is some interaction, a Hubbard-like interaction like VNI times NI plus 1, nearest neighbor, density interaction, right? So if you restrict to your nearest neighbor hopping and nearest neighbor interaction, you can actually show that this model is Bethe integrable in 1D. And then actually, if you look at a local operator like N1, N2, this is of course local, right? Because 1 and 2 are sites next to each other. Then you actually realize that ETH is not getting satisfied. This is this blue curve from exact diagonalization. And that is because, contrary to the expectation here, this OA does not go to a smooth curve. Okay, so this is rather scattering of lots of points like this. This does not go to a smooth curve. However, if you turn on next nearest interactions in this theory, then the integrability is lost. And then you actually come back to this red curve, which you can sort of imagine that if you could make the system larger and larger, would go to one smooth curve. And in fact, this smooth curve would basically coincide with your microcanonical or your canonical ensemble calculations. Okay, so that's the statement of ETH and its violation in the integrable limit. Another very interesting example which has been appreciated more recently is that of many-body localization, which is an interacting version of the famous Anderson localization problem, where again, ETH is violated due to some, again, emergent conservation laws, which are called L-bits. Again, if you look at the high energy part of your spectrum, and here to reach this many-body localization, you start with your, let's say, spin model, and you add some disorder field, like a random magnetic field to the problem, which is this axis, and you keep on cranking your disorder. Ultimately, there is a transition from ETH to many-body localization, and these many-body localized states, these high-energy eigenstates, are completely different in character to their ETH counterparts. Okay? And in both these cases, the violations of ETH happen because there's an extensive number of emergent conservation laws. By extensive, I mean basically the same as the number of degrees of freedom in your system. And the physical consequence of that is almost all initial conditions that you can imagine starting off with retain memory during dynamics. So that's the hallmark of non-thermalization, right? So in thermalization, basically, if you start with two completely different initial states, ultimately some bare bone memory like the energy density remains and everything else is washed out if you look at local quantities. Whereas here, the state, even after a long time evolution under unitary dynamics, retains a lot of memory of its dynamics, retains a lot of memory, and that's because there's an extensive number of conservation laws, okay? So this is one well understood route through which ETH can be violated, and in such systems, this right-hand side would not work. Something else would work, okay? Good. So let me take a short pause if there are any questions. Otherwise, I'll go on. So.
Now, in your case, you're saying that the integrability is from the Bethe in that sense, and not that there is infinitely many local conserved quantities, or which?
Right. So in the, okay, so I don't understand Bethe integrable systems all that well, especially in the quantum version. But the point is that even there, if you look at the eigenstates, all the eigenstates I think can be written in some quasi-particle description. So that's the key point. So this statement that I made, that all eigenstates have a quasi-particle description. So if you think about this problem, for most interacting theories, you can just do this for the states close to your ground states. Okay.
Right.
After a while, this quasi-particle description breaks down. But so Bethe integrable or not, the key property I'm looking at when I say integrable systems is this line, that all eigenstates have a quasi-particle description.
And that ensures that there is a large number of local conserved quantities.
Exactly.
Which then remain.
Yes.
Okay. And in the previous slide, if I may ask, if you go to the previous slide.
Sorry. Why can't I go to the previous slide?
So in the first equation, are you making a statement that at large time, because there is an energy gap, that at large time the blue part will go to 0?
No. This is more subtle than that.
Okay.
So if you imagine that, okay, this is quote unquote called dephasing. If you imagine that this dephasing only happens due to this addition of lots of these complex numbers, right, interfering with each other, then the time scale for equilibration. So what do I mean by equilibration? You understand this is equilibration. So this is roughly the time scale. Then the time scale of this equilibration would be basically the inverse gap, EI minus EJ, which is an incredibly large time scale. Okay. But if you look at an actual model calculation or even in experiments, because now people can do these things in experiments, actually you see that in most cases, the time scale is order 1 in natural units. So that's why I stress that this ETH of the off-diagonal matrix elements is equally important.
Okay.
Because, so that's an important thing. Okay.
Okay, thanks.
Yeah. So let me go on. So today, in whatever time I have left, I'll talk about another mechanism of ETH, which has come to the fore in the last couple of years, which is, can ETH be violated in translationally invariant non-integrable systems? So because I say translationally invariant, of course, I rule out many body localization, because now there is no disorder in my theory. And because I say non-integrable, of course, I rule out integrability. So both these well-known mechanisms, which I talked in the previous slide, go out of the window. So the question is, nonetheless, can ETH be violated in such theories? And in the past few years, 3 years or 4 years or so, people have understood this question better. And it turns out that the answer is yes in some cases. And that is called weak ergodicity breaking from some anomalous high energy states, which are called quantum many body stars. And these anomalous high energy states are actually embedded, if you wish, or peppered, if you wish, in an otherwise ETH-satisfying spectrum. Okay, so this is sort of a cartoon picture of this. So basically, you can imagine that your Hilbert space, or basically your eigenstates, break up into two almost disjoint sets. And that's why I have this approximate sign here, not an exact sign here. And one set, this blue set, is like the scar states which strongly violate ETH. And the other set are basically ETH respecting states, okay? And the dynamical signature of that is, while most initial states that you could imagine preparing in a lab for such a many body system thermalize reasonably fast, and go to the ETH predicted value, there are some initial states which actually do not thermalize. And they show some very anomalous dynamics, and that's the dynamical signature, and this is what is known as weak ergodicity. Okay? So...
Arnab, one question.
Yeah.
So presumably your scar states and the thermal states share the same part of the energy spectrum, right?
Correct. That's of course very important. Yes.
And so then usual way we think about when we have, localized states and let's say states which are extended, is that unless you are very fine tuning, if they are in the same part of the spectrum, and unless you're fine-tuning things so that they don't couple.
Yeah.
In general, the localized states will delocalize.
Correct.
So there's a symmetry which is protecting this kind of...
Good question. So the short answer to your question is not everything is understood, but let me give you a more precise answer. If you want an equality here, okay, then indeed you're correct. My Hamiltonian needs to be fine-tuned. But there are very good reasons to believe that if you want an approximate symbol here, which is of course an approximate statement, then there is a much larger class of parameter space that you're allowed. So,
I see. Okay, I'll let you go. Maybe the question will answer.
But so let me, so I'll sort of tell you two sort of mechanisms which are known in the theory, and then if it's still unclear, you can,
Sure, go ahead.
Right. So, okay. So there was this very famous experiment by Lukin and collaborators in 2017, where essentially they had a system made of Rydberg ions. One doesn't need to know the details because this is the only slide that I'll show where there are some details. But the important thing is that there were 51 of those. So if you want to imagine, there are like 51 spin degrees of freedom. So that's already a very large Hilbert space. It's roughly 2 to the 51. Actually, in this case, it's slightly smaller. We'll come to the reasons why. But it's already a very large Hilbert space. In that Hilbert space, Lukin and fellows, they did their experiment and they took several initial states which were at the same energy density. So in partial answer to Rajdeep Das' question, so these initial states that Lukin and others selected in their experiment, they were basically at the same energy density. So from ETH, you would expect that they would basically show the same thermalization property. But what they showed in their experiments was rather remarkable. While most of the initial conditions rapidly relaxed to the sort of thermal state that was expected, there was some very anomalous initial conditions which took much longer to relax. What was even more peculiar was that there were some persistent oscillations. Now, these oscillations are well known in quantum mechanics. In few body quantum mechanics, these are like, if you wish, Bloch oscillations or oscillations of a single spin if you put it in a magnetic field. But this is really much more surprising because this is a many particle system with a much larger Hilbert space, and you're starting with a high energy initial state. Okay, so in the Rydberg atom language, basically a Rydberg excitation was called 1 in their nomenclature, and a Rydberg ground state was called 0. So if you want to think of a spin half problem, then 1 is like an up spin in SZ basis, and 0 is like a down spin in the SZ basis, right? So then if you started with the Rydberg vacuum, which is basically everywhere the Rydberg ion is in its ground state, then this is, okay, so this right-hand side graph is actually a theory calculation from a model, which I'll soon introduce. Then this state actually thermalizes rather rapidly to the expected answer, which is this blue dotted line. However, if you start with a Rydberg charge density state, so what is a Rydberg charge density state, even though there's no charge here? So, so let's say the first ion is in its excited state, the second ion is in its ground state, the third is in its excited state. So it's like 1, 0, 1, 0, 1, 0, and so on. Or if you want to think in a spin language, it's a nail state in one dimension. I forgot to mention that the experiment was in a one-dimensional chain, okay, the system. Then something miraculous happened. Then what they could see in their experiments was that this 1, 0, 1, 0, 1, 0 coherently moved to 0, 1, 0, 1, 0, 1, which is its symmetry partner, and then again moved to 1, 0, 1, 0, 1, 0, and so on. So this is clearer in this picture where there are these persistent oscillations, which are remnant of, if you wish, Rabi oscillations. But I would again like to stress that this is really a many-body Hamiltonian with a huge Hilbert space. So this is completely non-obvious, right? And so this is the anomalous dynamics I was talking about from certain initial conditions, while most other initial conditions would show nothing peculiar. So what was the reason of that? So the reason was quickly realized theoretically to be quantum stars. So before I move to the many-body version of it, let me in one slide introduce the one-body version of it, which is much more well-known and well understood. So imagine you take a classical system like a particle which is in some stadium, and basically the only dynamics that it has is it's a free particle, and whenever it sort of hits the boundary of the stadium, it reflects. Okay, that's it. So suppose you take a circular problem like this, then of course we know energy is a conserved quantity, but because of the shape of the stadium, there's another symmetry, which is this circular symmetry, which leads to an angular momentum. So this classical problem is integrable. Basically what that means is if you start with two nearby classical trajectories, they do not disperse at very long times, okay? But if you deform the shape of this stadium, okay, I have forgotten what is the name of the stadium. It has some Russian name, but okay. If you deform it like this, then one of the conservation laws is lost, but of course energy is still a conserved quantity. But nonetheless, because you lose one conservation law, this becomes a chaotic problem in classical mechanics. And then if you start with two nearby trajectories, this is what this picture is trying to show. There are actually two nearby trajectories, but then of course you can see the effects of chaos. And after a long time, you cannot really make out what was close initially, right? Now, if you solve this problem in quantum mechanics, so this is a problem where again, you just have to solve some standing waves in quantum mechanics. Then you realize that most of the quantum states, if you look at the eigenstates, which you have to find numerically here, and you look at a particular eigenstate and you look at its amplitude square, so the probability distribution in real space, most of the eigenstates would be rather diffused in real space. This is not, by the way, but some of the eigenstates would be actually very, very anomalous in the sense that you can see some clear sort of enhancement of the quantum probabilities near some classical paths. So here you can obviously visualize the classical path, right? And these anomalous classical paths are also existing in this problem here, in the sense that if you really start with this exact classical path, then the problem just remains there, okay? So there are some unstable periodic orbits even in chaotic problems, and this is sort of the quantum version of it. Whereas if you look at the nearby eigenstates in this quantum problem, then you would see that, okay, those nearby eigenstates would again have their sort of weights diffused in this stadium more or less uniformly, okay? So this is sort of the one-body version of scars, and this was theoretically known from pioneering works by Heller, and this has also been experimentally seen. And so on. Okay? So now I come to the many-body version of it. So I again appeal to Lukin's experiment, and let's say we try to understand it using a minimal theoretical model. So here, the key ingredient turns out to be something called a Rydberg blockade. So all that you need to remember is that Rydberg blockade tells you that if there are two nearby or nearest neighbor Rydberg ions which are both in the excited state, then the system pays a huge energy cost. There's a huge penalty for that. So essentially, that means that if you have any two states being 1-1 and their nearest neighbors, to the zeroth approximation, if you're trying to do a theoretical model, you should disallow such states. Okay, that's what Rydberg blockade does to you at the zeroth level of theoretical modeling. Okay, so this is essentially what was done, and the consequence of that was some model called the PXP model. So this is again a model of spin half degrees of freedom living on a line. Okay. And the only thing that you need to take care of, which turns out to be a very important thing, is that now your Hilbert space is constrained. So what does that mean? As I told you, if any two neighboring spins are up, so you should imagine for concreteness that I'm drawing these in the SZ basis. Okay. So if any two neighboring spins are up, then you just kill that state. That state is not allowed in your Hilbert space. Okay. So that's why it's a constrained Hilbert space. So unlike a usual spin half problem, which would have 2 raised to the power L states if you have capital L spins, because of this additional constraint in your Hilbert space, the number of spins for a large spin system actually goes as the golden ratio to the power L, where this golden ratio is square root 5 plus 1 by 2. So that's some irrational number. And yeah, so that's the first thing you need to remember, that there's this constraint Hilbert space. So you cannot locally flip a spin most of the times, but sometimes you can locally flip a spin and not go out of the constraint Hilbert space. So when can you do it? So this is shown in this picture. So imagine that you're focusing on, where did I go? Yeah. Imagine that you're focusing on this red spin. So if the two spins on the neighbors of these red spins are down spins, then you can show that you can freely flip this red spin from up to down or from down to up. But if any of these other guys is not a down spin, you can show that one of the moves would take you out of your constraint Hilbert space. So that is the PXP model. So this model introduces quantum dynamics in this problem. So these projectors are just doing mathematically what I said. They're just saying that if you look at site I and sigma x obviously does this flipping of a spin half degree of freedom, then what really happens is you want this neighboring spin and that neighboring spin to be down. So that's what these projectors are doing here, right? And this is your quantum many-body system, okay? Of course, if these projectors were not to be there, then this is a non-interacting theory. The presence of these projectors makes it a highly interacting theory, okay? And now we'll try to understand what happens in this model. Okay, so this is our model. This is called the PXP model because there are two projectors and there's one X. So it's PXP. Okay, right. So this model has an interesting history. It was actually first introduced by Krishnendu, Subir, and Steve Gurman in 2002 when they were actually trying to understand the effective theory of bosonic Mott insulators in strong electric fields. And they also got some very interesting equilibrium phase transitions from that, etc. But of course, at that time in 2002, nobody was thinking about the dynamics of such theories, right? And it was only realized much later that the dynamics of this theory is highly anomalous. Okay, so what do I mean by that? So if you remember, I told you that most initial states in this PXP model, this is actual calculation from the PXP model, a numerical calculation using exact diagonalization. So most initial states in the PXP model actually thermalize like this. And by the way, all the initial states that I'm talking about for the PXP model, you can imagine them to have such an energy density such that their temperature is basically infinite. Okay. So if you want, I was talking about the microcanonical ensemble, and from there you can pull out a temperature for the equivalent canonical ensemble. So the temperature is infinite for whatever initial states I'm starting from here because of my choice of energy density. Okay, so so then you can ask, what is so special about this nail state, right? You can really ask that question. That the nail state is special is also shown here. So if you start with the nail state and you calculate its overlap with the many body state at time t and just take a mod square of that, which is known as the fidelity, then for most initial states, if you just focus on this green curve, for most initial states, this fidelity would just rapidly drop to 0 and stay 0. That's roughly like saying that your initial state sort of spreads very quickly in the many body Hilbert space. That's roughly like that. Okay, so your fidelity would just very fast decay to 0 and then stay 0. But if you start with your nail state, then this fidelity shows this very interesting revivals. Okay, so for the PXP model, forget this green curve for a bit, focus on the blue curve. For the PXP model, there are these persistent revivals like this, and they keep going. So a partial answer to Rajdeep's question is, remember I put an approximate sign there. So in the PXP model, you can add some terms to make this approximate sign to be almost exact. If you make that almost exact, then you get this green curve where the fidelity really returns to 1, and this is a many body fidelity. But of course, in the PXP model, this is only approximately true. So there is a decay of this quantity, but this decay is very, very slow. And if you imagine the microscopic timescale of this theory is 1, so this t is measured in the natural units. So you can obviously see that you can see a very anomalous dynamics, still a rather large time scale compared to the microscopic time scales of the theory. Okay, so that's what I mean by approximate scars.
So
Yeah.
in that notation, is it known? Presumably, this is governed by the coupling between your whatever the Néel sector and the thermal sector.
Exactly. Right. So I'm saying that there is a non-zero coupling, which eventually causes the state to spread in the entire Hilbert space. But nonetheless, there's a very large time scale which is generated in the natural units that you have. And so this is, of course, a perfectly observable consequence.
No, that I understand. But I'm just asking, is this coupling has some scaling with the system size, or is it just a number which is very small, turns out to be very small compared to the natural microscopic scale?
Right. So the answer is not fully known, but I think it's basically a number which is anomalously small in terms of the natural units.
But it doesn't scale with the system size or anything like that.
Well, nobody has done a very careful study, but what I told you is my gut feeling. I have some reasons to believe that, but okay. Yeah, it's not very precisely.
Go ahead.
Yeah. So, somebody might object and actually say that, okay, how do you know that your full spectrum is basically ETH respecting and it's you're not seeing an integrable model only, right? So the way to answer that is that you can look at something called the level spacing in the PXP model. So if so you don't need to understand the details of this Wigner-Dyson and this Poisson distribution. These are some universal distributions of level spacings. All that you need to remember is that for integrable models, there is no notion of a rather, for integrable models, there is a notion of a level crossing. Okay, so you actually see that there is a weight when S tends to 0. S is basically the level spacing going to 0. Okay, so S denotes the level spacing. Whereas for a non-integrable theory, there are avoided level crossings. So this P of S basically hits 0, right? And in the PXP model, you actually see the latter. So that's a strong numerical evidence that this PXP model is a non-integrable theory. And therefore, we are talking of weak ergodicity breaking and not some integrable limit. That's an important point. Okay? And of course, there's no disorder in the theory. So I'm not doing very well with time, but that's okay. So, so now, how do I know that these scars violate the eigenstate thermalization hypothesis? So again, let's say I do my exact anglization, and then if I look at the entire numerical data of this PXP model, let's say for size 32 spins, and the reason I can go to 32 spins here is because this is a constrained Hilbert space. So the Hilbert space is not growing as 2 to the L, but growing slightly slower than that. Of course, exponentially, but nonetheless slower than 2 to the L. Then you see that most of the states, so this color coding is supposed to denote that most of the states fall on this canonical curve or its neighborhood. And if you keep increasing the system size, actually almost all states would fall on this canonical prediction if you measure some local quantity in all the eigenstates. But nonetheless, you can see that these towers of states are emerging, right? And in particular, focus on these crosses. So there are order L of these special eigenstates, which really strongly seem to violate ETH. And the special property of these order L eigenstates is that all of these states seem to have a rather sizable overlap with the Z2 initial state. And that solves the mystery that why you needed to start with the Z2 initial state to see this anomalous dynamics. Whereas if you started with the Rydberg vacuum and you computed its overlap with the scar state, that's a rather small number. Okay, so clearly this anomalous dynamics is happening from the Z2 initial state because there is a very large overlap of this particular initial state with the this special band of states, which are almost equidistant in energy. So if you look at this energy difference, that gives you a time scale, right? And that is precisely this time scale that you see here, right? But this is a purely many-body effect. That's why it's called a quantum many-body star, right? And these states are highly atypical. So if I look at something called the half-chain entanglement entropy, so what do I mean by that? let's say I take any many-body eigenstate. I know the full eigenstate. So of course I know the full density matrix of that. That's just the outer product of the eigenstate with itself. Then let's say I integrate out half the degrees of freedom in my system. Then I get a mixed density matrix because there is some non-zero entanglement in my state. So I get a mixed density matrix for the reduced density matrix. From that, I just do trace of rho reduced times log rho reduced. So that's just the von Neumann entropy. So that von Neumann entropy, I'm calling the entanglement entropy. And the half chain is because I have integrated out half the degrees of freedom. So this entropy shows something called a volume law for highly excited states, which means that if you take any generic interacting model and double the number of degrees of freedom, let's say I'm in one dimension, then this entanglement entropy, just like usual thermodynamic entropy, would also double. So that's this statement, okay? But for these scars, which are also high energy eigenstates, numerical evidence points strongly to the fact that the entanglement entropy is highly anomalous. It just behaves as log of L, okay, instead of going as L. So this is highly sub-extensive, if you wish. So that already also tells you that these eigenstates are highly atypical. Okay, right. And as I was just saying that to the pure PXP model, you can again add some other terms. These terms also live in your constrained Hilbert space. I don't have the time to explain to you why the authors chose this particular crazy looking term, but there's some natural justification for that. Then you can actually make these quantum revivals. Now please focus on this green curve. So this green curve is with the small perturbation. So I'm calling it small because this H2 is roughly like 0.05. Then there is almost a perfect revival for at least 32 spins. Now, whether this remains in the thermodynamic limit, nobody knows. My expectation is that the answer is no. You would require even more fine tuning, but okay. So then you can ask, what is the possible mechanism for this? A possible mechanism for this. So one possible mechanism is that you actually start with a small corner of your Hilbert space, which is isolated by some symmetry of your problem. And then you sort of add a perturbation which breaks the symmetry, which we usually do in physics. I mean, as we normally know in physics, it's much more interesting. It's much more interesting to actually break a symmetry and see its consequences. So here also you do that, but you do this breaking of symmetry in a highly non-generic manner. So what do I mean by that? So I add a local perturbation in space which breaks the symmetry, but this local perturbation is such that this annihilates a particular corner of your Hilbert space. It doesn't touch that corner. Okay, so let me demystify this statement by giving you a very simple example. So consider again L spins living on a ring. So ring just means that you have the spins on a one dimension and there's a periodic boundary condition. Okay, now let me define a projection operator, almost like the projection operator I defined previously, sorry. But this projection operator lives on neighboring sites, I, comma, I plus 1. And remember that there is a periodic boundary condition there. Because I'm talking of spin halves, basically the natural projection operators to think of are either P singlet or P triplet. So here, let me focus on P singlet. So basically what P singlet does is, if you supply it with a singlet of the two neighboring sites, then that singlet happily passes through. But if you supply it with a triplet made of these two spin halves, then this P singlet kills that triplet, okay? And of course, it's very easy to construct such an operator. You just do 1 minus sigma I times sigma j, okay? And that's it, apart from some normalization factors, okay? Now, let me focus on the largest possible spin, SU2 representation of this capital L spin. So of course, that largest possible spin is capital L by 2. Then it's easy to see that this particular subset of states, which of course has capital L plus 1 states because the total spin is L by 2, is annihilated by all such operators. So no matter where your I, comma, I plus 1 is located, this space of capital L plus 1 states is annihilated by these projection operators. Okay. So now let me start with a very simple problem, a toy problem. So just a bunch of spins interacting with a magnetic field in the x direction. Okay, so that's a very simple problem, and you can just do a symmetry analysis and break this problem into lots of patches in your Hilbert space. Right now, you turn on a perturbation which breaks the symmetry. Okay, and the perturbation is like this. Okay, now see, this perturbation has this property that I require. Firstly, what is this v I minus 1 comma I plus 2? I have chosen these site indices to be different from I and I plus 1. That's the only thing I really need. And so I wanted to write the most local things. So therefore I chose I minus 1 and I plus 2. You could have chosen I minus 2 and I plus 3 or whatever. That's slightly non-local, but okay. And this can be a generic operator like this. Now you see, this full problem obviously does not commute either with the total SX operator or these bunch of spin singlet operators, right? But nonetheless, this corner of my Hilbert space, the corner which is untouched by these projection operators, is still the many-body eigenstates of this problem. So if I start with the initial state, which is, let's say, S equal to L by 2, comma, SZ totally equal to, let's say, the highest spin representation, right? Then, of course, that state would just do a perfect block oscillation, even though this is a many-body eigenstate of this problem, okay? So this is a possible mechanism. I have broken the symmetry of this problem in a highly anomalous manner, in a highly non-generic manner, okay? Now, in PXP model, this is most likely not the full story, because if it were to be the full story, then there would be no off-diagonal matrix elements here. This separation would be perfect, okay? But actually, most likely in the PXP model, there are very small non-zero couplings here, which connect states here in the scar sort of manifold to states in the thermal manifold. And that eventually causes a decay here. But in fact, you can show that this PXP model is very funny because you can add different perturbations. One perturbation I already told you, which actually enhances this Z2 revivals. But you can add other perturbations as well, which actually enhances, for example, Z3 revivals. They actually make the Z3 state, which in the original language is just a 1, 0, 0, 1, 0, 0, 1, 0, 0 state like that. It actually enhances the revivals of that, right? And then you can add some other perturbations which enhances the revivals of the Z4 and all. So this PXP model is almost like a model which supports loose embeddings of this multiple SU2 Lie algebras corresponding to distinct families of scars. And this is actually even true if you stare at your numerical data, because you see that there are lots of these unusual tower of states here, right? So yeah. So let me stop here and ask if there are any questions. Okay, so this is why I was sort of highlighting the fact that the PXP model really has approximate scars, but nonetheless, because these quantities, if you wish, the couplings to this thermal class of states is really, really small, you actually see all this consequences, right? And there is nothing very fine-tuned about the PXP model. It was a very minimal model that I came up with. So since I'm running out of time, let me not go into this. All I would want to say is that, you see, I started with a constrained Hilbert space. Now, there is one very natural place in physics where constrained Hilbert spaces appear. These are in Hamiltonian formulations of lattice gauge theories. And the constrained Hilbert spaces are nothing but the Gauss's law in your lattice gauge theory, right? So the PXP model, it was recently shown in this paper, is actually exactly equivalent to a particular lattice Schwinger model in one dimension. And basically that lattice Schwinger model is a U1 lattice gauge theory in its S equal to half or spin half representation. These kind of gauge theories are called quantum link models. And these are generalized lattice gauge theories with finite dimensional local Hilbert spaces. So spin half is, of course, a finite dimensional local Hilbert space. But nonetheless, the gauge symmetry is perfect in such theories. Okay? And this U1 gauge field is coupled to dynamical matter. And these matter are, you can sort of think of them as staggered fermions. And there is an exact map between the PXP model and the lattice Schwinger model, which I've shown in this picture. But unfortunately, I don't have the time to elaborate on this. Later, if somebody is interested, I can explain more during questions. Okay. So here, basically what happens is in the gauge theory language, this Z2 state is basically a flux state of electric fluxes where all the fluxes are pointing in one direction. Okay. So normally, if you start your state in such a flux state, you normally think of string breaking, and that is exactly what happens if you have a S equal to 1 version of the quantum link model. So instead of spin halves here, you just put spin ones, and you still have a kosher gauge theory. So if you take the S equal to 1 quantum link model coupled to fermions, then you actually have something called the string breaking here, which is sort of a well-known phenomenon in gauge theories with dynamical matter. Okay, but if you have the S equal to half quantum link model, then it actually shows coherent oscillations, which are very surprising. Now we know the reason of that. That's because of quantum stars. But this thing was actually noticed much earlier by Debashish and his collaborators in 2012. They also noticed that there is no string breaking in this S equal to half quantum link model with dynamical matter. Instead, there's this very peculiar anomalous oscillations, but they did not have the explanation of that at that time, because they also couldn't sort of understand that this was due to quantum stars. But at least they could really figure out very nicely in their paper, there's a well-known paper actually, that they had these anomalous oscillations. Okay. So now let me go to example 2, and I don't know, I'll ask the moderator, how much time do I have? So,
yeah, it's actually still 5, so you can have maybe 10 minutes.
Okay, okay. So maybe I'll take roughly 10 minutes to just explain the gist of the second.
We have another meeting at 5:30, so we should.
No, definitely. I'll be over much before that. Right. So now I started, Debashish and I started talking, and we asked the question that can we have an even simpler gauge theory? Okay. Where there may be quantum scarring. Okay. So what is an even simpler gauge theory? You just switch off the dynamical matter, right? So there is no dynamical matter. It's a pure gauge theory. So actually such a pure gauge theory is well known to us condensed matter physicists who work on quantum dynamo models and quantum link models and spin liquids. So basically, there is a way of defining a U1 lattice gauge theory without any dynamical matter on a ladder-like system with Lx and Ly, again with periodic boundary conditions in both directions. And here, this model is well known to condensed matter physicists because the gauge theory, the Gauss's law here is basically something which is called the ICE rule in condensed matter, which is the 2-in 2-out rule. So you see, I'm drawing all these pictures in the electric flux language, but basically the 2-in 2-out rule says that if you go to any side, because there is no charge sitting there, basically 2 of the fluxes come in, if you look at my pointer, and 2 of the fluxes go out. Okay. So that's a theory without any dynamical matter. And now you can put all kinds of terms here which respect this 2-in 2-out rule. And all such theories are perfectly kosher gauge theories. Okay. So one particularly well-known theory here, again, also well known to quantum condensed matter theorists because of quantum dynamo models and quantum link models, is the so-called Rorschach-Iverson-like theories. So there is one term which is off-diagonal in the electric field basis, and there's another term which is diagonal in the electric field basis. So what is the off-diagonal term? So you go to each elementary plaquette. So each elementary plaquette is a square now, right? So you go to each elementary plaquette, you see if the fluxes have a clockwise or a counterclockwise circulation. Now, if there is a particular circulation, a well-defined circulation, you just reverse the circulation like this, as I've shown here. Whereas if you go to a plaquette which does not have a well-defined circulation like this, then O kinetic acting on that plaquette just gives you 0. Okay, so that's the kinetic part. And in gauge theory language, that's just the magnetic flux operation. Okay, because that's like the minimal off-diagonal term you can write in the electric flux basis, the most local term. Okay, so that's like a magnetic term or a B square term, if you wish. Okay, so secondly, I also wish to add a O potential, which is diagonal in my electric flux basis, and in my spin language, this is just a counting term. So all that I'm doing is I'm again scanning my lattice. Wherever I see a plaquette which is perfectly flippable one way or the other, I just increment my O potential by 1. You can imagine it as a counter or whatever. And whenever I see an elementary plaquette which does not have perfect circulation, I don't increment my O potential. So O potential is necessarily an integer valued quantity. Okay, so that is going to be important in what I'm going to say. And this lambda is some parameter. Some particular well-known limits of this theory are lambda equal to 0. This is very well known for some three-dimensional quantum spin liquid which Hermele, Fisher, and Balance proposed. So there lambda is essentially 0 and it's a three-dimensional model. If lambda is -1, that is also a very well-known point. That's called the Rockshire-Kivelson point. But anyway, I'm looking at this theory at an arbitrary lambda. Okay, so let me be quick and just tell you the physical picture.
Arnab, your potential term counts both the clockwise and anti-clockwise flux in the same way.
Exactly.
It doesn't give a -10.
Yeah, correct. So it just increments the counter by +1.
Okay.
Yeah, so this is the usual way in which you define quantum link models or dynamo models. In fact, I won't be explaining things here, but there is a very simple way to go from quantum link models to quantum dimer models. And much of what I'm going to say also holds true for quantum dimer models, but for lack of time, I won't explain that. Right. So let me stress the mechanism here, which is, I think, very interesting. Okay, so this is the mechanism. So let's first focus on lambda equal to 0. So I switch off this coupling. So that just means that I have only the magnetic term in my lattice gauge theory, right? So then what you can show is if you look at the many body spectrum at lambda equal to 0, first thing you can prove, which is easy to prove, is that that spectrum has a E to -E symmetry. What that means is that if there is a many body eigenstate at +E, there is necessarily another many body state at -E. That is an easy statement to prove. But what is much more interesting, which actually happens due to an index theorem proven by these two gentlemen first in 2018 in a rather beautiful paper, which I encourage all of you to read. What you can actually show is that there are exponentially many exact zero modes which live at E equal to 0. But I just now told you that the spectrum is symmetric about E equal to 0. So these zero modes don't live in the ground state. They actually live in the infinite temperature energy density of your theory, right? Because they are mid-spectrum states of a spectrum which is E2 - E symmetric, right? So that's why I have highlighted it like this. At lambda equal to 0, due to this index theorem, there is an exponentially large subspace of zero modes. When I say exponentially large, I mean exponentially large in system space, exponentially large in number of spins. That's what I mean, or the number of degrees of freedom. So this is the zero mode subspace, and there is a bigger exponentially large number of zero modes. Okay, and due to this index theorem, basically I can block diagonalize my problem into zero modes and non-zero modes. Okay. However, when I turn on a finite lambda, then this index theorem is lost. Then, of course, naively, you would expect that these zero modes would hybridize with the non-zero modes. And that is indeed true. Most of the zero modes hybridize with the non-zero modes. But remarkably, what happens is that there are some very special directions in the zero mode manifold of states. So remember, any linear combination of zero modes is also a zero mode, right? So there are very special directions which are marked with these red arrows, which Of course, by definition, are eigenstates of O-kinetic, in fact, with eigenvalue 0, but they are also miraculously eigenstates of O-potential. Therefore, they are eigenstates of the full Hamiltonian. And these eigenstates actually survive as quantum many-body scars, whereas everything else of the zero-mode subspace hybridizes with the non-zero modes and form an ETH manifold. By the way, this is also doubly surprising because you can show that in these zero modes, if you pick arbitrary directions, they'll satisfy ETH. You can actually show that numerically. And only these very special directions do not satisfy ETH. Now, what is really nice in this gauge theory example is you can turn on a local electric flux term, which actually provides a natural pinning term to pin these special directions, which are also miraculously the directions which lower the entanglement entropy and therefore make the states anomalous. And that's why these things survive as quantum stars. Okay, good. So, so I won't go into much of the details, but let me try to just specify the important points in 5 minutes or so, and then I'll conclude. So, so as I said, the quantum scars are linear superposition of lots of zero modes, and the zero modes are things which are present at lambda equal to 0. Okay. And these special linear combinations have two properties. This is trivial, that O kinetic acting on this gives you 0 because it's a linear combination of zero modes. But what is much more non-trivial is that O potential acting on this gives you an integer times the same state. And why an integer is important? Because as I said, this O potential by definition can only have integer eigenvalues. And therefore, by definition, this H of lambda at any arbitrary lambda has this state as its eigenstate, right? So with the eigenvalue lambda times n, right? So a simple argument already tells you that these anomalous states necessarily violate ETH. Why? Because imagine the mid-spectrum part of your theory, that mid-spectrum part has very small level spacing, right? Exponentially small level spacing. So what that means is, if I change my coupling in my theory from lambda 1 to lambda 2, then what really happens is a many-body state here and a many-body state here looks completely different. That's what these different colors are supposed to signify. However, these special states or these special linear combinations are completely unchanged, as I have just proven to you, even though there are lots of neighboring energy eigenstates floating around. So that's why these states are necessarily anomalous. The second thing which is really remarkable about these states is, even though, as I said, most of these zero modes or almost all of these zero modes are highly delocalized in your Hilbert space. So this is a sort of an abstract Fock space representation. Even though most of your many-body zero modes are highly delocalized, these special linear combinations are actually highly localized in Hilbert space. Okay, and there's a very precise notion in which it's localized, which I can explain later if someone is interested during questions. And so I see that I'm running out of time. So, but I think I have already given you the gist of it. And let me just show you some numerical evidence that there are indeed these these anomalous quantum scars. And these anomalous quantum scars are highly special linear superpositions of these zero modes, which stay as true eigenstates of the problem at non-zero lambda. And the way you know that these are scars is because they are outliers of both the half-chain entanglement and also of local correlation functions. So this is like an electric flux correlation. These scars are outliers here, whereas the neighboring states satisfy ETH. Okay. Then the other thing which I wanted to stress is, as I said, this quantum many-body scar is a complicated superposition of these zero modes. In fact, if you write out this superposition, and if you are a Monte Carlo guy, you would think of these weights as being generated from a pseudo-random superposition of these zero modes. But actually, there is nothing random about this particular superposition. This is highly structured. Why is this highly structured? Because actually, if you calculate something called the Shannon entropy, which tells you how localized or delocalized a state is, then even though the individual zero modes are rather delocalized in Hilbert space, as delocalized as the neighboring states, these special linear combinations are much more localized in Hilbert space, which is what this is supposed to show, that this S1 of the quantum scars is much, much lower than the S1 here. And there are various other ways of showing that. That's why this is almost like order by disorder, but in the Hilbert space, okay? Because there is an exponentially large manifold of states, you turn on a small lambda, some very special directions have been stabilized, whereas everything else is mixed with the non-zero modes. And these very special directions have this additional property that they are much more localized in Hilbert space in a very concrete mathematical sense. Okay, and as usual, there is this memory effect in unitary dynamics. So if I start with some simple states, I start with lots of simple states actually, which have the same energy density. In fact, I start with 6,433 initial states, and I just show 2 of them. Even though the initial value of whatever local quantity you are looking at is completely different, because those initial states sort of thermalize, you see that after some time scale, they sort of go to the same final value. This is the hallmark of thermalization. However, there are 18 quantum many-body scars at this dimension of the system that I'm looking at. So I'm looking at a particular ladder with 56 quantum spins. So for that ladder, there are 18 such special states which have a sizable overlap with these special quantum many-body scars. And then you can see that these states don't thermalize, which is the signature of quantum scars. And these quantum scars also, we have preliminary evidence that they also exist in wider ladders and most likely in 2 dimensions as well as in 3 dimensions. In fact, the story gets much, much richer in 2 and 3 dimensions, but unfortunately, I don't have the time to go into that. And I'm running out of time, so I just flash my conclusions here, which you can read. So basically, this quantum many-body scars are a very rich subject, and there's lots to be understood there. And there are multiple mechanisms to generate these quantum scars. I just showed you 2 of the mechanisms here, and a deeper understanding is needed here. And I truly believe that approximate scars are much more common than perfectly fine-tuned scars, because you see both the PXP model and the U1 quantum link model, they were very well-known models, right? You saw that the PXP model was known originally from 2002 as a minimal model for bosons in their Mott phase in a uniform electric field, in a tilted electric field, whereas the U1 quantum link model without matter field was also very well known right from the pioneering work of Salish and Wiese and even before that. So there was nothing very, what should I say, complicated about these models. But now we realize that their spectrum is highly anomalous, right? So I don't believe that this is a highly fine-tuned property. And I didn't have any time to explain another equally interesting story in what happens in periodically driven or fluke systems. And there again, there is some very interesting things about scars and also the melting of scars. And that's something which is also a very interesting thing. But let me just stop here and thank you for your attention and take any questions or comments from you. Thank you.
Can I ask one question?
Yeah, sure.
Hi, this is Kedar. So this fact that you have these specially chosen directions at lambda non-zero, presumably this extends, this is not a perturbative statement in lambda, right? This extends all the way up to lambda equal to 1.
Correct. Yeah.
And
in fact, Kedar, just one comment. These graphs are at lambda equal to 1. Okay.
And at lambda equals 1, there's usually a kind of a correspondence between the quantum dynamics and some effective Markov chain, right?
Correct.
So what does, yes. So what does this imply for that?
This is a slightly tricky question because if you want to sort of stretch the Henle picture into dynamics, then you see that you need to talk about imaginary time correlations. But the unfortunate bit is unitary dynamics is completely different from imaginary time dynamics, as we know from Monte Carlo, right? So it's not immediately clear what the implication of the Henle picture might be, because that is for imaginary time dynamics only.
So there's no analogous correspondence you can make for unitary evolution that exploits the presence of these scars. That's what you're trying to say.
Yeah, so I have thought a bit about it. The answer is not immediately clear to me.
Okay.
Maybe there is a way, but yeah.
That would be very interesting.
Yeah.
So Arnab, given that you have some directions that are left as zero modes essentially, even when you turn on lambda, is it possible that there is still some index theorem which people have not thought about?
No. Because
So
no. No. So as I said, when you turn on finite lambda, this index theorem is broken. But nonetheless, these red lines are no longer zero modes because now your E2 minus E symmetry is also lost in your spectrum. So you cannot classify zero modes. But these directions are nonetheless very special because no matter what your lambda is, these directions are unchanged, which is already enough to tell you that these are anomalous eigenstates, which is what I sort of showed in this picture.
Okay.
So Arnab, it's a very interesting set of results. I was just thinking that is there any like a similar things in the classical analogs of the system, like in classical stochastic systems? Like it is kind of, we know that there are these exclusion processes where certain initial conditions are known to preserve for a large time, that they don't decay anymore. They just stays in the configurations. So for example, if you take a TASEP with 1010 and
I understand.
So is there, so those models have
so let me give you so of course I don't know the full answer, and there's a but my hunch is that the way you should think about it is think in terms of transfer matrices, right? And then probably some of the things that we learned here can be sort of what should I say, translated into that language, right? And
No, but I guess if I ask the reverse question, which is perhaps what Tridib was implying, I mean, we know a lot of kinetically constrained models in classical dynamics, where just because of the kinetic constraints, some things can't move in some directions, right? Or some things can't change. Now, the question is, if I make that dynamics quantum, typically one would expect that goes away, right?
Naively, you would expect that. Yes. Naively, you would expect.
So these are not just quantum analog. This is not as simple as
exactly. That's by the way, Kedar. Since you raised this question, see, I talked about these zero modes and non-zero modes, right? And this index theorem and these special directions. See, of course, I use the example of this U1 quantum link model, which is a constrained spin model. But these index theorems are valid even for unconstrained Hilbert spaces. So I'm not actually claiming that this story does not work even in unconstrained Hilbert spaces. And there is no classical analog of jamming or something, right? So so it's more than that.
It's more than, right.
Last question. So, I mean, in some sense, when Feynman wrote down, wave functions for bosons and stuff like that, which has nothing to do with any of this, there was the single mode approximation type stuff he wrote down, right? Now that's of course not an exact eigenstate of the bosonic Hamiltonian, but is this in some ways looks like has a relation with such single mode approximations.
So let me answer that question. So this particular slide, I don't know how to obviously relate with your comment. Probably there is no obvious relation, but But as you can see, I'm still thinking about lots of aspects here, so I cannot answer in definitive terms. But let me go back to this PSP thing. Here, what you're actually saying is basically true. So there is something called spectrum generating algebra. And basically what that means is that there is a corner of your Hilbert space which sort of is protected from the rest of the Hilbert space, even though that corner is sitting in a, what should I say, exponentially dense soup of eigenstates. And in that corner of Hilbert space, there is a local operator which you can repeatedly act to make eigenstate, to make, what should I say, coherent excitations. So remember I said that in integrable models, all eigenstates have quasi-particle descriptions. So
Right.
in the PXP-like models, the quantum scars have quasi-particle-like descriptions, if you wish. Yeah, but this picture is not always true. So I don't know any obvious way in which this picture is true here.
Here, okay, I see. Okay, thank you.
Yeah,
I see. Thank you. Yeah, that's very interesting.
Okay, so I guess we can all thank Arnab. Maybe you can unmute and clap.
Thank you.
Very
Very nice talk.
thank you.
Great.
Thank you, everyone. Yeah.